Okay, cool. So if you got no question, let me just give you this very last section, which is I just want to give you a brief history of how this diffusion models got developed. We started with talking about score matching, right? And those score matchings are also there out there. I mean, there are also trials where people try to use a score matching to generate diffusion, but they are not very happy stories. So you can take a look at the results, but they cannot be extended to practical data sets, really. But they show something for dummy data sets. The very first result, which was quite impressive or was giving us something meaningful, was the original DPM work. So this is the one which you have in 2015. And at that point of time, people talk about diffusion. They think of this as a diffusion, but they don't think in terms of, the physical diffusion which we had. So people started to clarify the connection quite later in 2019, 2020. Here in 2015, they were just thinking of variational inference. And what they did in the original work, they had some simple CNN architecture. That CNN architecture was somehow fed by the embedding of time. So you get your time. This is what you do in your assignment 3. I think this is what Mohammad Riza did for you today and the last session. So you get the time, right? And then you just come up with one idea, like sinusoidal functions are the basic ones, but you can even put one neural network. This going to get the time and then compute you one embedding for time, right? So you think of time to be your token, then you get one vector, which is the embedding of that token, right? And now you have this embedding. You're going to inject it everywhere inside your neural network because you want your neural network be heavily depending on the time, right? So you get the time, you just do embedding, and then you add it everywhere in every single layer that you have. Maybe you can concatenate it with your available feature map. Maybe you just add it to that. Maybe you do another sort of computation. Whatever you want to do, you just somehow inject it everywhere. So that was the idea. So it was a very basic neural network taking the XT, the noisy sample, and then giving us back the mean value. In the very original one, they also learned the variance, but then they say it's not that much crucial to learn it or not, so they drop it later. Okay? So, but you can learn both mean value and variance. They are all of the same structure, same dimension as your data. And then the only difference here is that you're going to put some embedding trick here, and then you give your time to every layer, right? So this is the only change that you do. And then they started doing that. So they had a bunch of very cool experiments in that. So one of them is this famous Swiss roll data set. So you have the Swiss roll. You want to see whether you are going to learn this or not, right? So the diffusion process, if you put it on this basic process, alpha x xt minus 1 plus 1 minus alpha noise, right? And you keep on going in time, then you're going to see that you start with a roll, then gradually it's going to get more and more noise, and at some point it's going to be pure noise, right? And now you start from the pure noise, you move back using the model you learned, you trained, that neural network. And when you move back, you gradually see that this noise is going to scatter and somehow diffuse back into the architecture, which looks pretty much like the initial roll, right? So the cool part of this example was that they could eventually also plot the drift term. So you remember that when we write down the diffusion process, we always have a drift term plus some Brownian motion, right? And they looked at the drift term. You see that here it doesn't say too much, right? But as you get very beginning of time, you see that it's strongly taking you on the Swiss roll, right? Anywhere else that you are on this plane is going to move you. So these directions are the directions that are going to take that point towards the other point, right? So this is going to take you, I mean, when you add all of those drift terms, this is going to strongly take any sample here towards this light region, right? And this is exactly the Swiss roll. So you can really see the diffusion. Like those samples that you had originally in this plane are the particles, right? And somehow they are getting into a sort of very strong magnetic field, and they are starting to look like the image you want, right? Because that magnetic field is just drifting everything towards that structure. So this was the basic result. They had some result on MNIST, CFAR, other things, but they were not like the benchmark at that point of time. So if you read the paper, you see that they are not beating GAN or VAE or anything. So, but what they say is like we can, for the first time, we can use diffusion to somehow get numbers which are close to the benchmark. So this is the claim that they say. And the work was somehow left for pretty much 4 years up to the point when DDPM came out. So DDPM was the first serious implementation which could really beat everybody else. So in the DDPM structure, as I said, so they just wanted to estimate noise. So this idea that instead of directly or generally estimating or learning the mean value of the process, we can learn the denoiser or the noise component. This was initially proposed in this work, and for implementation, they used a UNet. This is pretty much the base implementation that nowadays everybody uses. They had a UNet, so the unit was the same unit as before. Again, the only difference was that we get the time and we do some embedding of time, right? So you get your particular time, you just do embedding, any embedding that you want, and then you inject it on every layer of the unit, right? So your input is heavily depending on time, and this is the most important thing you need to consider when you are doing the implementation, okay? So they did this one, and this actually worked quite well. So the first thing was that they could really see the diffusion process, right? Starting from pure noise, then gradually over time, you're getting into the image you want, right? It was a very nice demonstration. You can see, I mean, if you read the paper, they actually do all the possible not all the possible but most of application you have in mind. Like you want to just in-paint an image, you want to just get two images and combine them and get a new image with features of both. It's very interesting. You see like two faces coming into the model, and gradually over time, they are somehow mixing towards the point where you see a kind of totally new face with features of the both faces in it, right? So it was a very nice demonstration. And the key thing, which just very famous, was the fact that they could now generate very high quality images, which was not possible before. Okay? So this was the DDPM idea, and after DDPM, a bunch of works came out that they started to somehow improve the DDPM. I mean, they are, as compared to DDPM, less, say, innovative. They are more into the practical aspects. But this 2021, I guess, paper is quite famous because they have done a very sophisticated way of tuning everything. So actually, they had two key ideas. One of them was that they were efficiently learning the variances for reverse diffusion, which was very good because it was somehow improving the time efficiency, and at the same time, it was improving the quality, one point. And the other thing was the time scheduling. So they somehow indicated that considering how this alpha t is changing by time is quite important when you want to sample. So it's good that you just find a right scaling or scheduling for the time component. And they could somehow, they pretty much compared with anything that was at that point of time. And even though, I mean, you can see that it's still not beating everybody at that point of time, right? But it's getting close to the very much to the most state of the art, right? And they also compared it to the original work, the DDPM work, which you can see here, like they have significant improvement, right? So significant difference in the, here is the negative log likelihood, so the one which you want to minimize and make it close to 0, right? Okay, so that was it. And these are most of the research papers and research models that have been implemented, but people started to implement this also for commercial purposes. And the famous one is the stable diffusion. developed in LMU Munich. So the group was using diffusion in order to just get a prompt, text, or anything that you have, and then convert it to a kind of image that you want. So you just write down there, I want image of a cat with glasses, and then it's going to give you image of a cat with glasses. So how exactly you can inject that prompt into the model, I'm going to talk about it in the next part, which is, I mean, you can quickly catch it, understand how it works. But for the moment, the thing that we want to talk about is the diffusion process. And the key point about this architecture was that they were doing the diffusion in the latent space. What does that mean? That means that, say, for instance, for the moment, you want to just generate an image, right? You don't consider this first part, which is the prompting, right? The text that comes into it. You don't need this one right now. So I want to just get image X, right? I want to sample that one. And the way that we did this in DDPM was that we get X, we noise it, we just learn how to denoise it, right? But they didn't do that directly. So they get X, the image, they use variational autoencoder to go into the latent space, which is much smaller as compared to the original image space, right? And then in that world, they start to do the diffusion. So they get the latent representation of the image, they noise it, and they learn how to denoise it, right? Now, if you want to generate a new sample, you're going to sample something in the latent space. So this ZT, Z capital T, this guy is actually your latent noise, pure noise in the latent space, right? And you start to diffuse reversely in order to make it the latent representation of your image. So the Z that you see here on the left side, this guy is not eventually the image itself, but it's latent representation of it, right? But since you have the autoencoder, you are able to get from the image space to the latent, and you can get back from latent to the image space, right? So you learn what is the latent representation, then you generate your sample. So this is what we call it latent diffusion model, LDM. And pretty much most of commercial things you have are LDM because it's easier for you to work in the latent space, right? This is much smaller as compared to working really in the image world. So this was the stable diffusion. So you can check their website. I mean, and the paper itself is also interesting in details. And there are also a bunch of other things. For example, DAL-E, you probably have heard of it by OpenAI. So it again uses diffusion. We do, I mean, it's again latent diffusion model, but it's not exactly using, you know, the DDPM style diffusion. So it's pretty much doing a bit of innovation there, but the key point again is that you're going to get your text, you're going to embed it, you get into the latent space, and from that one you learn how to diffuse into your image, right? So this is the key idea, but I mean the details you can check it out. I mean, even though there are not too much details on this one out there. And also there is one Google version of it, Imagine. And this Imagine eventually what it does again diffusion. But the key point about the Imagine is that this guy is not doing it in the latent space. So it's not an LDM anymore. And because of that, it's computationally more expensive. So it somehow does exactly like DPM and DDPM. It works directly in the image world. So these are the samples, just have heard of them. Maybe if you're interested, you can learn more about them. Just to wrap it up for this part of the course, so probabilistic diffusion is eventually the version which is working, putting it that simple, right? So you can think about diffusion in general. This is what we tried to do in this chapter. And all those previous versions ended up with the current one, that's true, but the one which is right now working is probabilistic one. And basically what they do, they think of it as variational inference, and then DPM is the major class which does this, so it's going to learn the reverse diffusion by maximizing the evidence lower bound. And DDPM is the particular one which is the most efficient one, the most efficient one known to us right now, which is working much more efficiently as compared to the general form of DPM. And this is basically estimating the noising process. The key point here is that sampling is still an issue, right? And sampling is the same issue as we had it in the energy-based models. Because if you think about it, in energy-based models, if you wanted to sample, you had to use Langevin algorithm, right? And you were again diffusing, right? So for sampling energy-based models, you eventually are doing the sampling by diffusion. So this is as complex as that one, definitely, right? But the key point here is that there are a bunch of tricks here that we can do. So in the energy-based model, we just think about the general energy model, and that makes the story a bit complicated because you just get that one, put it as a score, and start to generate. But here you can do tricks like DDIM, right? Because you explicitly know the diffusion process, so you're having more degrees of freedom in simplifying the sampling one, the sampling algorithm. So one key point that you should keep in mind about the diffusion is that diffusion models are somehow scaling slower with the complexity of your data set. And what do I mean by that? I mean that if you think about, like, here is a simple data set, here is a complex data set, and then I'm talking about the amount of computation that you need to spend in order to just train your model, then in the classical model like VAE or GAN, the more complex your model data gets, like if instead of MNIST you are talking about ImageNet, then you eventually getting much more complexity, right? So it's going to boom up, right? So the more complex your data is, the complexity of your computation is going higher, right? But you can think of the diffusion models to have the same behavior with much slower slope. Like in the MNIST world, it's much more complex as VAE training, but when you want to train it for a very simple, a very complex data set, like high quality images, then it's going to be much easier as compared to the VAE. Okay? So this is good in the sense that if I want to deal with a complex data, then I can use this diffusion process to efficiently train a model sampling from that data, right? Because at the end of the day, the only thing I need to learn is how to start from noise and diffuse, right? And since this is a kind of pretty much fixed amount of complexity for any kind of data that you have, because any data that you have at the other side of time, you start from the same noise and you start to just subtract that additional noises from that noise, right? And this process is pretty much looking the same for MNIST and high-quality image, right? Because of that, I only need to know denoising, so I'm not really directly trying to find out what is that image. And this is making it like easier when the data is very complex, right? But the downside is that you cannot easily do this with simple data set, right? So it's a crazy choice if you want to learn MNIST, CFAR, things like this, and you go for diffusion, right? Because those data sets are so easy that you can eventually train a very simpler model that can do the quality that you want, right? So it's a very important thing to understand that when you want to use diffusion model, you should really make sure that the data set is complex enough that training a diffusion model is worth it, right? So it's like you cannot get to that quality with any other model. Okay, any questions? No question? Yes?
Like lower res pictures, and they looked all right, but were you sort of putting it as like it wasn't able to generalize as well?
Yes, this is the point. And if you try assignment 3, you see that, I mean, even you cannot really, by DSM, you cannot really train it to build and write down an 8, right? Yeah, whereas when you use VAE with much simpler architecture to just sample from fashion MNIST, you're eventually able to generate some meaningful samples, right? So this is totally the case. So if you want to really make it work for diffusion, you need to have significantly complex network. But the point is that that complex network is going to be okay when your data is very complex. Yeah? Okay. Questions?